I think it's recording. So hello everyone. My name is Suraj Jaiswal and welcome to the sixth tutorial of the course entitled Simulation of a Mechatronic Machine. In today's tutorial, we will be modeling a simple hydraulically actuated system. So if you can see the animation, this is just to give you a brief idea like what do you mean by simple by hydraulically actuated systems. So as you can see, hydraulic actuation of the mechanical system will help you to get your work done. So we will be modeling a very simple hydraulically actuated system. So let's proceed. These are the list of contents that I will be covering. First, there is a requirement for the add-on for our Simscape multibody. So we will be needing a Simscape multibody multiphysics library. And then I will give you a brief introduction about what are the requirements for our system, and then how we can model the mechanical system and the hydraulic system, can carry out the coupling between the two different systems, and then I will show you the results. So before proceeding anything, I already have my MATLAB open. So we need an add-on package. If you go to this add-on, it's a good idea to just cross-check whether you have it already installed or no. So try to search for multi-body, multi-physics. So you see this one, it's already installed for me. If it's not installed for you, you can go ahead, click this link and do that add an installation. If not, you can simply open this folder, but be very careful which version of MATLAB you are using. I am using MATLAB 2019A. So I want to install this zip file. So be very careful with what version you have. Okay. Once you open this folder, it will navigate you to the folder where it installed. For me, I actually installed it over here. Over here, yeah. So I double click this. Then I need to do the startup underscore sm underscore ssci dot m file. I need to open this m file and run. It will, okay. It's because I'm not within this folder. Now when I try to run, yeah. So it will automatically open this Simscape multibody multiphysics library window. You can just close it. It has set the path for you, so it's fine. You can close this window and navigate to the folder where you want to save your file. So for me, this is the one. And then I can simply type smnew in order to open a new Simscape multibody file. Okay. So these are the basic components there. So let's go back to our slide and see what is our system and what are the requirements for it. So if you see the plot over here, you can see not the plot, but if you can see the simple hydraulically actuated system, you can see it's a combination of two systems. One is the mechanical system, which is this part, and the other is the hydraulic system, which is this part. For the mechanical system, what are the requirements? So by default, we need a ground, inertial reference system or the global coordinate system, and gravity, right? So these are the three basic requirements for a mechanical system. Then we need three bodies. As you can see, this body one, body two, and body three. And then we need three joints. So joint J1 connecting between ground and body one, joint J2 between body 1 and body 2, joint J3 between body 2 and body 3. And note that body 1 and body 2 are actually cylinder pistons, so they are cylindrical bodies. And about the hydraulic system, uh, it's a very simple circuit that we have it here, where the basic components are pump and the tank, and then we need components such as directional control valve over here. It's a 3 by 2 directional control valve. It means that there are three ways. So there are three ways to connect it to the circuit, and there are between two ports. So either pump will be connected to this port, or this port will be connected to the tank. And obviously this directional control valve will be controlled by by a valve control. So there is some valve control which we will also model it. And then there's a hydraulic actuator. In this case, it's a single acting hydraulic actuator. So we will model this hydraulic system separately and this mechanical system separately. Then in order to couple this, we will simply connect this hydraulic actuator to the end of this prismatic joint between joint 1 and joint between body 1 and body 2. So if I explain this coupling in a very simple term, it's like we are calculating the dynamics of the hydraulic system separately, and then using this force actuator, the force that is generated from the dynamics of the hydraulic is fed into the multi-body part, and then uh, the rest of the system behaves accordingly. So this is the most simple explanation I can give you about a coupled multi-body and hydraulic system. So basically we take the hydraulic force from the hydraulic dynamics and put it into the multi-body system. So if you have understood this part, that's most of the part is done. The rest of the tutorial is just simply uh, modeling the systems as we have been modeling in our previous tutorials. So let's go ahead and model the bodies. So let me go back to the Simscape multibody file. Before proceeding anything, it's a good idea to save this file as you want it under any name, under the same folder where you navigated in the MATLAB workspace over here. Okay, so by default, we already have the solver configuration and other components. So this world frame already takes care of the ground and the inertial reference system. Okay. For the gravity, by default, the software assumes gravity in the negative z direction. But for us, uh, we want it in the negative y direction. So if x is horizontal, y is vertical, and z is coming out of the plane for all of us, then let's change the gravity from minus z to minus y. Okay. If you go to this display and hide automatic names, it will show the names for all the components. So that's a quick way of doing it. Let me move these things away so that we don't get confused. Okay, so we will be using this solid component block. Let's rename it as body 1 and it's a cylinder. If I double click this, then the shape will be cylinder, radius will be 40 millimeters, so 0.04 meter, and length will be 400 millimeters, so 0.40. Press enter and then F5 or this option here for updating the visualization screen. So this is our body. In the inertia, we want it to be calculated from geometry based on density. Density will be that of steel, which is 7,800 kilogram per meter cube. Update this derived values. Then in the graphics, I want it to be red in color. So this is red, green, blue code. So I increase the R value, press enter, F5. And then frames, I need two frames on two ends of this cylindrical body. And by default, there is this frame R at the center. I don't need it. Press F5. Then I go to this new frame. Let's call it the bottom frame B. It should be based on geometry and the bottom of this one. So select this surface, use selected feature, center of bottom surface, press save. Then again, I need another frame on the top. Let's call it T based on geometric feature. Select the top surface, use selected feature, center of top surface, press save. So our two frames are ready. Just be very careful that the length of the cylindrical is about the z axis. Okay, and for us, uh, uh, I mean, in the overall system, for us, the coordinate system is something like x is horizontal, y is vertical, and z is coming out of the plane. So just note that. Later, I will show you how to do the transformation. Press OK. So our body one is ready. Similarly, you can simply select, press Control and drag to have our second body, which is a piston. Double click this. The only difference is this time the piston is has a different radius, which is 30 millimeter. So change it to 0.03 meter. Press enter, then F5. Inertia properties will remain the same. Derived values, you can just update it. If you have copied the previous body one, everything should be fine. And in the graphics, I want it to be this time green in color. So let me change the RGB green value to be more than the other. Enter an F5, and the frames will be taken care of automatically. So no worries. Then we need to press OK. So our body 2 is ready to. You can shape the blocks as you want. Uh, it's nice to shape it, but it's not a requirement, of course. And then we need a third body, which will be again based on this solid component block. We will call it body 3. Double click this, and we want it to be cube in shape. So shape will be brick. Dimensions will be 400 millimeter each side. So 0.40. Okay, press enter and then F5. Inertia properties will be calculated from geometry based on density. Density will be that of steel, which is 7,800 kilogram per meter cube. Derived values, you need to update it. Graphics, I want the graphics to be blue in color. So RGB, I increase the blue value, press enter and then F5. And for the frame, so by default, there's a center frame in the middle. Um, Now, as a good modeling practice, since it's a cube, it will not make a difference. But as a good modeling practice, it's always good to see how you're modeling the system. So this system will be oriented like this in our actual system, in our overall system, right? Because this is X, Y, and Z is coming out of the plane. So we want the frame on the bottom of this, on the bottom of this cube. So let's make this port R invisible and define a new frame based on geometry. Let's say it's the bottom, and this is that surface. So use selected feature. Centroid of minus y surface is what we want to select, and then press save. If you try to see the isometric view, don't get confused when you see this B frame on this side. You just need to see carefully how is this X, Y, and Z oriented, and then press OK. Let's rotate this. So we have our body 1, 2, and 3 ready. Then let's go back to the slide to see our joints. So basically we will be needing uh, 3 joints, out of which 2 will be weld joint. So between ground and the cylinder, which is body 1, there will be a weld joint, and between piston which is body 2, and body 3 will be a weld joint because those are like fixed joints. And then there will be just one prismatic joint or a translational joint between body 2 and body 3, so between cylinder and piston. So let's go back to our model. Of course, the first weld joint is optional because you can simply connect the body one with the world reference frame. It should be okay, but in most cases solver might end up giving you some error, so it's a good idea to include the weld joint. So let's say we search for weld joint. Let's say this is joint 1 and rename it. We will use the default property as it is. You cannot simply connect weld joint with body 1 because remember body 1 is oriented or defined in such a way that the along its z-axis, the length is along its z-axis, right? So if you double click this, if you simply connect this without changing its orientation, it will be connected like this in the overall system, right? But we want it to be connected like this, something like this, right? So you can do it in two ways. Either you can go to this bottom frame and change the frame axis here, orient it as you like, but we won't be doing that. We will be using rigid transform because it's always a good idea to have a separate component block for such transformation so that you know instead of defining it within the component within the body component block, you might sometimes forget whether how this bodies are oriented. That's why we use rigid transform such that the base frame will be connected to joint 1 to world frame and the follower frame will be connected to body 1. So if you double click this, the rotation method we will be using aligned axis such that the follower frame such that the z axis of the follower frame, which will be connected to body 1, should be projected onto the y axis of the world frame, right? That's what we want. And the y axis of the follower frame can be on the, let's say, the x axis of the world frame. So this is how we are going to define our first rigid transform and press OK. Let's rename it to rigid transform 1. Perfect. Now you can make the connections. It's fine. Okay. Now we need a prismatic joint between body 1 and body 2. So let's search for prismatic joint. Let's rename it as joint 2. It's a prismatic joint. And orient it using control R. This joint will be between body 1 and body 2. And remember that this joint will be oriented in a prismatic joint since body 1 and body 2, this frame T and frame B both are along the z axis, so it's fine. uh, you can simply make the connections, but if you see the plot, the figure here, piston needs to be inside the cylinder at a distance 350 millimeter along its axis. How we can do that? We can do that by using rigid transform. Let me show you. Yes. So let's search for another rigid transform. Let's call it rigid transform 2. Orient it using control R. We want this joint to be inside the cylinder along its axis. So if you double click this rigid transform, translational method, and in this translation standard axis method along the local z axis, this distance should be minus 0.35 meters, so 350 millimeter, and press OK. this joint needs to be at this distance inside the cylinder. So once you have done that, I think it's fine to make the connections as shown, and then obviously it will be connected to body 2. Similarly, as for the first body, the connection between first body and the ground, we use rigid transform. Similarly, we will use another rigid transform to make the connection between body 2 and body 3, because body 3 is oriented properly as we want it to be. But before that, let's have another weld joint. Let's call it joint 3. It's a weld joint, and we want, let's use control R option to orient this. It will be connected here. Let's not make the connection yet. We need rigid transform, another rigid transform. It's fine to use the same rigid transform as the first one till the time the follower frame is connected to the cylindrical part of the body. So basically this piston. So let's orient this such that follower frame is connected to the piston. I think I mixed up with the connections. Just a minute, I'll make some space. Yes, that's fine. So now we have our mechanical system ready. If you simply go ahead and simulate the system, obviously you need to press this. Okay, first let's stop it. Initial condition. I mean, at time t equals to 0, if you press this Y up and front view, this is how our system looks. Let's see the frames and the center of mass. This is how we have modeled our system. And it looks good to me. This is how we wanted our system to be. So the mechanical part is fine. Now we'll just play the animation and see if the movement is defined as it should be. So the moment we play the animation, we see that body 2 and body 3 just slides under gravity. Obviously, it will go like it will fall down because we have not defined any other constraint. But this is just to check that our mechanical system is working properly. Now we will provide a hydraulic actuation to this. So for that, we need to define a hydraulic system. Let's go back to the slide. So I already showed you how the mechanical system will look like. So in order to, okay, so let me go back to my model. So if you remember carefully, what are the things that we require for hydraulic system? We require some basic components such as the pump and the tank. Pump is basically we will be using a constant pressure source, and tank will be some atmospheric reference. And then obviously we will need to define some hydraulic properties, some fluid properties. So let's go ahead and do that. So you need to go to this library browser. Under library browser, you need to go to Simscape, Foundation, Hydraulics, and then Hydraulic Source. Here you can find this constant hydraulic constant pressure source. You can simply select and drag it to the workspace. Then you need a tank. So for that, you can go to hydraulic elements. Hydraulic reference is what we need. So it acts as a tank. Hydraulic reference. Once you have these properties, we need to define fluid properties as well. So if you go to hydraulic utilities, custom hydraulic fluid. If you see my presentation, the detailed path are shown here. so that's fine. You can follow the presentation, pause the video and follow accordingly. But let me define some properties for the hydraulic constant pressure source. If we double click this, we want the pressure to be 150 bar. So 150 into 10 to the power 5 Pascal. You can change the unit as you like, but let it be Pascal. We change the unit accordingly. E5 means 10 to the power 5. Okay. And press OK. In the hydraulic reference, you don't have to do anything. Now in the custom hydraulic fluid, double click this. Uh, we want the fluid density to be 850 kilogram per meter cube. We will increase the kinematic viscosity to be 32 into 10 to the power minus 5 meter square per second. Bulk modulus, we want it to be 1500 megapascal, and we do not want any relative amount of air trapped, so we can make it 0. And absolute pressure below absolute 0 should be marked as warning. If the pressure goes below absolute 0, it should come as a warning. Okay. So once you have defined this fluid properties, you can simply press OK. So our basic components are ready. Next, let's see what we require. So now we require a directional control valve. In order to define a directional control valve, we also need to define the valve controls or the valve actuator, right? We are using a 3 by 2 directional control valve. What does that mean? That means, as I already showed you in the beginning of the video, that there are 3 ways between 2 ports are possible. And it needs to be modeled along with the valve control. So how we can do that? Let me show you. So if you go to library again, this time you need to go to Simscape, then you need to go to fluids, then under hydraulic isothermal, inside that there's a valve, and inside the valve there is this valve, not this directional control valve, directional valves. And we want to use this 3-way directional valve. So just copy it. Then again, we need a valve actuator. So we have this valve actuator. We will be using this valve actuator block. Fine. In the directional control valve, let me define some properties. So most of the properties will be as it is by default, but you can cross check if you have some other property. And also remember that we will be modeling ideal directional control valve. So basically there will be no leakage. So for that, let's see the properties. So the area characteristics will be identical for all flow path, and model parameterization will be maximum area and opening, right? In the leakage area, it will be 0 meter per second per 0 meter square because we don't want any leakage. And the flow discharge coefficient can be as it is, which is 0.7. The laminar transition specification should be based on ratio, and the laminar flow pressure ratio can be 1 into 10 to the power minus 3, 1e minus 3. Press apply, fine. Then under model parameterization, maximum opening can be as it is shown, which is 0.005 meter, and opening area can be, let's say, 2, 2.25 into 10 to the power minus 5 meter square. Okay. These values are already given in my slides, so do not worry about it. And the valve opening offset will be 0 again because obviously we don't want any leakage. So we don't want any offset. and then press OK. So our directional control valve is fine. Now in the valve actuator, so try to understand this thing. The valve actuator actually provides a sort of signal to the directional control valve, which helps to say the directional control valve whether it should be which way will it be, way 1, way 2, way 3. So accordingly the circuit will be connected, and this is provided in a form of voltage signal which ranges from -10 volt to +10 volt. Okay, and also for that we need to define some properties. So let's say the valve stroke is as it is. We will change the time constant to be 0.001. Yes. And then actuator gain can be 5 into 10 to the power minus 4 as it is, and press OK. So once you have defined the valve actuator, directional control valve, you also need to define a signal. So input signal to this valve actuator. How do we want the actuation to be? So for that, we need to use a signal builder. So if you have followed my previous tutorial, I have already showed how to make find the signal builder. You can go to Simulink, sources, in the library, go to Simulink, sources, and then the signal builder. So we will be using this signal builder. So under the signal builder, we need to define how it should be. If you follow the presentation, so the signal builder will be something like as shown here. It will be +10 volt between 0.3 to 0.5 second and -10 volt between 1 to 1.8 second. And other than that, it will be 0 for a signal between 0 to 3 second. So this is how the signal should be. So we will define the same. Let me go and define it quickly. So I click this and I say it is, let me follow these slides. Yes, now I can model. So for 0.2 second, it's 0. Then if you need to define new points here, you can simply press shift and go to this the signal builder and click. It will define a new point. So it's a good idea to make multiple points. It's fine. Now let's go to this point. So between 0.3 to 0.5, it's 10 volt. 0.3, it's 10. Enter 0.4, it's again 10. Enter. Then between 0.5, it should be not 0.4, 0.5. Then between 0.7 to 0.8 second, it's again 0. So 0.8, it's not 7, that's 0, and 0.8. I hope I'm defining it correctly. If not, mm, what am I doing? Okay, then between 1 to 1.8, it's -10, 1 -10, enter, and then between 2, it's 0 again. And obviously, we want it for just 3 seconds, and but this signal is for 10 seconds. So you can go to Access, Set T Display. You can change it to 3 seconds and press OK. So this is how we want our signal to be, right? You can simply close this window. Now, if we go back to the slide, we need another component, which is a hydraulic actuator. So what does hydraulic actuator do? As I already told you in the beginning, uh, it is used as a bridge between the multi-body system and the hydraulic system. In general, it's a double-acting hydraulic cylinder or a hydraulic actuator, but in this case, we will be using a single-acting hydraulic cylinder. So basically, we will define hydraulic actuator where the dynamics of the hydraulics are computed and the resultant force will be fed into the joint of the multi-body system. So basically joint 2, which is a prismatic joint, and it will be connected parallel with that joint. And the specification of this hydraulic actuator or the dimensions will be similar to the dimensions of the cylinder piston for the mechanical part. So basically the dimensions of body 1 and body 2. So let's go ahead and model that. So for this hydraulic actuator, you needed that multi-body multi-physics library as an add-on. So if you go to the library, you need to go to the Simscape multi-body multi-physics library, then hydraulics, and then we need to use this hydraulic actuator multi-body. If you have installed the add-on correctly, this adding this component into the work into this empty space on the screen will not be a problem. Obviously, it's showing some unrecognized function or variable. I will show you what it is. Let's orient it such that like this. So this is how it will be connected parallel to this joint. Okay, so let's define some properties for this. Before that, so this port A will be connected to the directional control valve port A, and this port B, obviously it's a double acting hydraulic cylinder, but we won't be using the other half of or the other half the other port. So for that reason, we'll connect this port to the tank, which serves as the best reference. So it will become a single acting. And this base frame and follower frame will be connected parallel to this base frame and follower frame of joint 2, which is a prismatic joint. So if you have understand that connection carefully, let's go ahead and model. So piston area will be pi r square. R will be that of radius, which is 40 millimeters, so 0.04. And whereas for the piston rod side, it will be 0.04 for the cylinder and 0.03 for the piston. So 40 millimeter and 30 millimeter are the radius. Stroke length will be 0.30 meter, which is 300 millimeter, and dead volume side A. So basically this side, dead volume means the volume of uh, the pipes and the hoses that is making the connection amongst the hydraulic components. So let's say uh, that is 8 into 10 to the power minus 4 meter cube. Whereas for side B, which will be connected to the tank, let's say it is 1 into 10 to the power minus 4. Obviously, this will be very small because we are not using it, so that's fine. It does not make much of a difference here. And then chamber volume will be varying because it will be hydraulically actuated, and press apply. In the hard stop, you can change the damping to be 1500 Newton per meter second, whereas hard stop stiffness can be as it is 1 into 10 to the power 9. Press apply. And then under friction, The breakaway friction or the static friction can be 1 into 10 to the power minus 9. So 1e minus 9. And same the Coulomb friction or the this, dynamic friction. It can be the same value over here. This breakaway friction velocity, I think it's the Strybeck velocity. Normally it is that. And then we have viscous friction, which can be 10 to 1 into 10 to the power minus 6 Newton per meters per second. So yes, this is how our system is. And press apply and then press OK. Once you have done that, we have defined our all the components required. So what we need to do is we need to make the connections as shown here, right? So let's go ahead. If you remember the first figure in the requirement, not the figure, but the system. So basically the pump is connected to the directional control valve. So connect this with the pump. And the tank is connected to also the directional control valve. So this T port can be connected to the hydraulic reference. The pump also needs to be connected to some reference point, which should be tank as shown here. I'm just making space. Then obviously the fluid needs to have some properties. So using control R, orient this and have this hydraulic fluid properties over here. Fine. Once we have done that, then this uh, directional control valve needs to have some hydraulic actuation, which will be provided by this valve actuator like this. And okay, I think it's fine. And obviously there needs to be some signal builder that is provided to this valve actuator. And what can be, let me make some space. And if you just connect the signal builder to the valve actuator, it won't connect because the signal types are different. So for that, you need a Simulink PS converter because the signal builder provides you a Simulink signal, whereas we need the signal for the physical system. So you don't need to change any properties here. You can use it as it is as the default values, and then you can just make okay, you can just make the connections. Okay, so you have defined the directional control valve as well. It needs to be connected to the hydraulic actuator such that port A is connected to this end and port B is connected to the tank. Okay. So once you have done that, you can just simply go ahead and make the coupling between the hydraulic system and the multi-body system. Once you have done that, things should be fine. If we just go ahead and simulate the system, let's see what happens. And obviously we have provided the signal for 3 seconds. So let's simulate it for just 3 seconds and press run. Let's compiling. Let's see how is the animation. So if we play, you can see something happened. So it actuated the system and then it lifted it up and then it lifted it downward, lowered it down. It lifted it upward and then it lowered it down. So this is what we were expecting, right? So things are fine. I mean, we have done the coupling between the multi-body and the hydraulic system. So great news for us. But at this point of time, I'm very much interested to see how are the pressures uh, in the hydraulic chamber, the piston side of the hydraulic chamber, or how is the volume flow rate, and also how is the position and velocity of this prismatic joint. But before that, it's always a good modeling practice to go to analysis and see, go to Simscape and then see the statics viewer to see the degree of freedom. Are there any redundant constraints or not? So if we go to the multi-body part, we can see the degree of freedom is 1. There are no redundant constraints. Everything looks fine. And obviously, there are other systems as well. So things are fine. If we go to analysis, Simscape, and variable viewer, you can see the variables that are there. Okay. So let's see, sense the pressure and volume flow rate in this part of the hydraulic circuit. So side of piston chamber of the hydraulic actuator. For that, we need to use hydraulic sensors. So for that, you can need to go to library. You need to go to Simscape, foundation library, hydraulics, then hydraulic sensor. So hydraulic pressure sensor is what we need. And the next we need is a hydraulic flow rate sensor, correct? So the hydraulic pressure sensor needs to be connected in parallel with the circuit. So suppose we want to sense pressure A connected to this port, and it should be with respect to a reference. What can be the best reference than the tank atmospheric pressure? So this is connected like this, and the volume flow rate is connected such a way. Let's orient this. It is connected in series with the circuit. So since we want to sense in this part, we can simply make the connection such that this A port is connected here, and then this P port is connected to this part of the circuit. Don't try to mess up. Try to make your circuit and your connections clean so that you don't get confused. And obviously, if you double click, you can sense the volumetric flow rate as well as the mass flow rate. So for that, you have this M and Q. We will be using this volumetric flow rate Q. And obviously, you need a PS Simulink converter and a scope to see the result. Let me make some space. Okay, so let me rename it as PA. So pressure in the chamber side. I always like to have this nomenclature done properly. You can simply copy paste this for the volume flow rate. Perfect. Then you can simply make the connections, pressure to the pressure converter and volume flow rate to the volume flow rate converter. Is there any other way? Okay, just see the connection properly and don't get confused. Similarly, we want to sense the position and the velocity of this joint as well. So if we double click this joint too, we want to sense the position and the velocity and press OK. So it will open this position and velocity port. Correct. We can use the same converter. We can copy paste it here. We'll rename it as this is for position and this is for velocity. You can make the connections accordingly. Do not get confused with the circuit. I think I might have. Yeah. And also, if you need to sense, uh, if you want to lock the signal, you need to right click the signal, lock selected signal. Similarly here, lock selected signal. Now, if you simulate the system again, let's simulate. We can see the position. For example, this is how the position looks like for the prismatic joint. Obviously, it starts with 0 because the way we have connected the hydraulic actuator with the prismatic joint helped us to define the 0 position. Similarly, we can see the velocity as well as the pressure as well as the volume flow rate. We can see the volume flow rate is quite similar to the input signal that we gave. But one important thing that I would like you to notice is this velocity plot and the pressure plot. If you see at the very beginning in the velocity plot, you see this oscillation. The same oscillation can be seen in the pressure plot in the beginning. This is not idle. I mean, uh, this basically defines that in the beginning, the initial conditions are not set properly, right? If you go to the analysis and SimScape variable viewer, so why is this happening is because uh, the mechanical system we defined it properly, but in the hydraulic system we don't know what will be the initial pressure in the system in order to maintain the cylinder and the piston in that position. So if you see this pressure, it's actually 0 in the beginning, and for that reason it is causing that problem. It should not be 0, it should need to have some value, right? So how we can find that value? Let me go back to the slide to just give you a brief idea about what I'm trying to say. So I already showed you how the circuit will look like and how the animation will look like and how are the plots and what are the regions that we need to focus on. Now coming back to what I was talking about, uh, the initial condition. So when the initial condition is not set, we need to set it and find the static equilibrium in the beginning. So what is static equilibrium? Static equilibrium is basically the value of the system at time t equals to 0. For example, in our case, the exact piston pressure is not known in the beginning, and this is causing instability in the system. So we need to get rid of that instability. How we can do that? There are a number of ways to achieve static equilibrium. Uh, First is the steady state manager is what that we are using in this tutorial. And then the other techniques are optimization algorithm and then one click solution from the solver configuration. That is the most easiest one, but it will be implemented in the upcoming tutorial, not now. So in the next slides, I will show you how to do that. But if you have installed the default packages, then everything should be included. All these options you don't need to worry about. But if there is any problem, you can troubleshoot it using the steps I have shown here. Basically, what installation needs to be required, or what other install requirements are there. So let me show you a very one-click solution and why it will not work this time. But it will be implemented in future, so do not worry. It's the most simple one. So if you go to the solver configuration, there is this option, start simulation from steady state. If you click this and press OK and simulate the system again, ideally it should work. But in our case, it is not. Now you see the pressure, this P, the value changed to be something like uh, 10 bar. Yeah, it's changed something to 10 bar. But if you see, let's see the pressure plot. Even now, there is this problem. There is oscillation. Why? Is because if you see the warning here, it says that uh, solver configuration block specify that the simulation needs to be started from steady state. However, Simscape multibody does not currently support this option. It will ignore this setting. So we are not able to achieve that. So let me uncheck this box and let me show you how we can do that. We can do that using this steady state manager. So if you go to analysis, control design, steady state manager, it will open a new window and you need to click this trim specification. What this will do, it will upload the list of variables. It will upload the list of variables, right? In a space, and it will automatically synchronize the values with the model. Now, do not get worried when you see so many variables. These are the variables that is defining your model. So basically, we know everything in our model except the pressure in the piston side of the chamber at time t equals to 0. So we will click this known except this pressure block, this chamber pressure A. We do not know its value. We can guess its value. Let's say uh, its value is uh, let's say 2 bar. It's not 2 bar. It's actually in this case, in this version of MATLAB, I'm not very sure, but these values are tens of bar. So when I enter 2, it's actually taking as 20 bar, something like that. I'm not quite sure about it, but we are just guessing a value to be like, say, suppose 20 bar. And we need to define a range. What will be the range for this? Whether it will be uh, uh, how should be the minimum and the maximum value? The minimum value will obviously be 0. It The pressure should not be negative, and the maximum value will be uh, the maximum pressure available at the pump. So 150 bar. So we have defined our guess value, which is 20 bar, and then minimum and maximum value as well. Now, what we need to do is we need to go to this trim option. In the optimization method, we need to go to this non-linear least square with projection. You can try different options, but in this tutorial, we will be using this option. The rest of the values can be as it is default, so do not worry about it. The tolerances are good enough here. Press OK. Once you have done that, you need to click this trim. The moment we give this trim, let me close this variable viewer window. So the moment we execute that, it will generate a report. Do not worry about when you see these red markings. Okay, let me go back to the slide. So this is, I just explained you, and this is what I'm explaining. So I will just keep it as a reference for me on my left side. So this is what the report generated. Do not worry uh, if you see red values here. What this report actually does, it actually gives you the achieved values for the variables, those were not set or those needs to have this static equilibrium. So if you see this pressure thing, the actual value is 0.99114 bar, I think. So this is the exact value what we needed. There are two ways of doing that. You can simply use this, set this value in your model manually, or you can do this automatically by clicking this set initial conditions. But do not get worried when you see these red options here. You need to read this report preview statement. So trimmed operating point for untitled search finished as operating point specifications were successfully met. So report was successful, but still these red marks are there. You need to see these values and think whether it's making sense or not. If everything is fine, then you need to press this set initial conditions. It will automatically send these initial conditions value to the model. Once you have done that, you can close it. You can even save this steady state manager. So I want to save it. Yes. Let's say it's model underscore steady state session. So once we have done that, it should be fine. Now let's simulate the system again. So now when you simulate the system again, before anything, see the variable viewer window, see this pressure P. This is 991135 Pascal. So basically 9.9 bar, something like that. Yes. Yes, this is 9.9 bar. And if we see the pressure plot, you see it's stable now. It's so accurate. There is no oscillation. The same thing can be seen in this velocity plot, correct? Whereas the position and volume flow rate will not make much of a difference because they were not making such a loud oscillation, but it's fine. If you see the animation, you can't see any difference, to be honest. It will still remain the same, but the differences can be seen on the plot. If you go to the data inspector, now let's plot our pressure with respect to, say, suppose what we had in when it was oscillating. Yeah, this is the one. So something else is also open. I don't know what. Yes. So now when you see the pressure plots uh, with no steady state and with steady state, you can clearly see like there is so much difference between the initial condition, and because of which there is a slight amount of difference during the first half of the simulation. Whereas the other half, if you see the later part of the simulation, it's kind of very much similar. So no changes there. But the initial part does make a difference. Similarly, for the velocity plot, if you see, these colors are so weird. Similarly, for the velocity, initially you can see where the oscillation disappeared, right? Whereas for the positions, no significant difference can be seen. It's almost the same. I'm just changing the color. It's almost the same. In the initial part, there might be seen some oscillation, something, a very small difference. So no difference there. So that's all I think. Let me go back to the slide to see if I've missed anything or not. I already showed you this part. I already showed you there will be no difference in the animation, but the plots will be, there will be difference in the plots. So That's all for this week's tutorial. But just a quick uh, troubleshoot trick. Like if you by somehow close this file and try to open the file again, it might give you some sort of error that unable to import the report or something like that. For that, you need to go to this model configuration parameter under data import and export. You need to uncheck this load from workspace. You need to uncheck these two boxes so that it will not load the reports. So, and once you uncheck this and click OK and then simulate the system again, it should work fine. So you need to do that trick. Once you will uncheck that, the start values will go back to the start values of the components you defined. So not the static equilibrium condition, but that's the quick trick. But other than that, I think that's all from my end for this week. If you have any questions, you can either email me or you can simply ask me in the comment section of this video. And if you like this video and if you feel that this video was helpful for you, give it a thumbs up and do uh, share and subscribe to the channel. Uh, just a thumbs up is also fine. It's a motivation to make more videos in the future other than this course as well. So till then, have a good day and thank you so much.